I'm in SPSS and I'm looking at the Hong Kong height and weight dataset, and we're going to look at linear regression. At the moment in the dataset we have several samples taken from the much larger dataset from when we were looking at confidence intervals. We don't need all of these, so if you like you can select all these other variables and just clear them. All we really need is height and weight for one sample. So to start off with, we'll just do a quick graph. We'll have a look at a scatter plot. That's fine. So we want the predictor variable, the independent variable, to go on the x-axis and the response variable to go on the y-axis. It doesn't really change the relationship. If there's an association between them, you'll see it either way. This is just convention that we plot the response variable on the y-axis. Now, we're also interested in fitting a straight line through these data points. So we can do this graphically. If we go into the chart editor, you'll see we have a little option down here which says Add Fit Line at Total. If we click that, you'll see here we have the option to fit a linear, which is a straight line, through here. Now later on we might be interested in trying to fit a curved line, and then we might tick quadratic, but in this case linear is fine. Close, close. So this is the picture which shows what's going on. It even gives us the regression equation here and the R-squared, which is almost all the output we need. But we're going to run the regression anyway and have a look at the residuals. So we go to Analyze, where are we going? Regression Linear. Our dependent variable or our response variable is weight, and our independent variable is height. Let's look at some of the options. Oh, I've lost my window. Hold on. It pops up on my other screen. So give us, that's fine, plots. Just tick these ones here, the histogram and the normal probability plot, and that will let us check for normality. Now we're going to need to save our residuals so that we can look at them. Unfortunately, SPSS doesn't have the option to automatically produce the 4-in-1 residual plot that which Minitab does, which I have to say is very handy. So you're going to have to do a little bit more work if you're in SPSS. So save the just save the unstandardized predicted values. So these are the values that the model is going to predict. So if I say I've got a person of 66 inches, this is the value that the model will predict for their weight. With the residuals, however, I think it's easier if you look at the standardized residuals, so tick that box there. Continue. Now, do we want any other options? No. Won't worry about that. Okay, that should do us. So, as usual, it's given us far too much information. Let's have a look at the graphs first. Are the residuals normal? That looks pretty good to me. Not perfect, but pretty good. So that's a histogram, which hopefully you can read by now. This is what's called a normal probability plot, and it gives you a straight line here. Now if the residuals are normal, then they will fall on this straight line. That's all you're looking for. Now this looks approximately normal to me, and usually we would look at both of these together, and hopefully between the two of them you can make a judgment call about whether the residuals are normal enough. There is a test we can do, and if you want to look that up you're welcome to, and it's just a test of normality. I'm quite happy for you just to look at the graphs in this case. Now there's a couple of other things that we're interested in looking at when it comes to the residuals, and so we want to just do a couple more plots. Now if you have the worksheet open, you'll be able to see the other plots that we're after, and it's a case of remembering what to do, seeing as it doesn't do them automatically for you. Now the first one I'd like to do is have a look at the predicted values versus the standardized residuals. So I'm going to go into Chart Builder, and you can see that here we've got the PRE stands for predicted values. The RE and this next one stands for residual, and the Z stands for standardized. I will understand completely if you don't think this makes any sense. Now what I would like to do is have the predicted values along the x-axis and the standardized residuals on the y-axis. So this is telling us, based on someone's height, what is the value that we're predicting for their weight. And the residual is the bit that's left over that's not accounted for in the model. And we want these errors just to be random. We don't want any patterns in here. Now there's a couple of things that you can see with this plot. One is you can, if there is let's say a curved relationship rather than a straight line relationship, you can probably see it in your scatter plot, but it will probably pop out a bit more clearly in this plot, and we'll have a look at that with another data set. And the other problem that will show up in this plot is if you have what's called increasing variance, and that might happen when you have very small errors with the lower values and the errors get increase as your predicted values go up, and we'll also see that in another data set. In this case, these look fairly well scattered about to me, so that's fine. Now the last plot that we might want to look at is the residuals, all the errors in the case order, in the order that the observations were collected. And this can sometimes show up if there was any, let's say, things that changed over the course of the experiment, if there was any drifting or increasing errors as the experiment progressed. So to do this, what I want to plot is these errors, but against the case number, so that's the row number down here. Hopefully these have been entered in the order that they were collected. And so what I will do here is, it's not easy to get this out, but in the legacy dialog box you'll see it's got what's called a line chart, and we want a simple one, but we want it of the values of individual cases. We don't want summaries. So click that and define, and the line represents our standardized residuals, and the category label is just the case number. Okay. So with this plot we're also looking to see that the errors are randomly scattered about, and in this case they do look randomly scattered. There don't appear to be any patterns in here, so I'm quite happy with all of this. So I'm happy that the assumptions are satisfied in this case, and so now that I've looked at all the assumptions, I'm going to go back and actually look at the output for the regression equation and see what that's telling us. So we have here variables entered, height, not very interesting, model summary. Okay, so I would like you to use the adjusted R-square, which is very similar to the R-square value. It just has had an adjustment made based on the sample size. If you have a large sample size, these values will be very similar. If you have a small sample size, your R-squared is going to drop a little bit. And that's just to say we can't be quite as sure that we're explaining all the variation we think we're explaining, because we don't really have a very big sample. If you want to look into that more, you would look up what's called overfitting your model. It's not usually a problem with just one variable, but if you, when we get on to general linear models, if we start putting lots of variables in there, it can become a problem. So at the moment, just look at the adjusted R-squared value. Now it gives it to you as a decimal. If you want to convert this to a percentage, you just shift the decimal place 2 points. So 0.273 would be 27.3%. And this tells us that we are explaining 27.3% of the variation in weight based on our model using height, which I think is pretty good, because we know that a lot of things are going to influence how much you weigh apart from your height. So there's going to be diet and exercise and genetics and all sorts of other environmental factors. So the fact that we can explain nearly 30% of the variation in weight just based on height, I think is pretty good. So that's sort of a measure of how good our model is at explaining what's going on. You can ignore the ANOVA table for now. You'll see that there is a test going on here, and this is just testing to see if the whole model together is significant. I'm not really too interested in that. What I'm interested in is the coefficients. So here we have the constant, which is the intercept for the model, which is also not particularly interesting. and here we've got the height. We have the B stands for beta, and this is the coefficient, and you'll see this in, where is the regression equation? It doesn't give us the regression equation. You can work out the regression equation from these coefficients, but it's nicer when it writes it out for you. So if we go back up to the scatter plot where we fit the line at the total, you'll see here we've got a regression equation. So y, which is weight, is equal to this constant term plus 3.51 times the height. And these two values here, these are our beta values, and this is what shows up in our table down here. So this is the constant, and this is the 3.5. Now you'll notice here they wrote this in scientific notation, so it's got an E. E2 is basically 100, so it means you multiply by 100, so it might be easier to ignore this particular format of the equation and look down here, it's written it out. So the hypothesis that's being tested here is that this coefficient is actually 0. Now if the coefficient for height is 0, that is equivalent to saying that there is no relationship between weight and height. That's equivalent to saying that the line is actually flat, and it doesn't matter what height you are, you still could have any weight. So that's a no relationship hypothesis. Now we have a very small p-value, so we have very strong evidence against that hypothesis, and therefore we can assume that there is a relationship between height and weight. And we know that that relationship is capable of explaining about 27% of the variation in weight. So we're looking to see, is the variable a significant predictor, and if it is, how much of the variation in the data can we explain? So that is simple regression in a nutshell. What I would like to do is look at a couple of other data sets just to see what happens when things go a little bit wrong. So I'm going to open up the car data set, and this was looking at the original price that cars were bought for and the advertised price for resale. If I go to Graphs Chart Builder, we can have a look at a scatter plot, and I'm interested in, does the original price predict the advertised price? And I would expect that the higher you bought a car, the higher the price when you bought the car, the more you're going to try and resell it for. So I would expect to see a linear, I would expect to see an increasing relationship there, and hopefully it's linear, a straight line. So again, we can fit the regression line here. We're clicking that one. Let's go for a straight line. Close, close. It gives us the regression equation. It doesn't tell us what's significant though. We have to do the analysis to get the p-value out. It does give us the r squared, which is about 60%, so that's pretty good. So it says that original price is predicting about 60% of the variation in the advertised price. Now we do have a couple of outliers here, and these are probably going to cause us problems. Let's do that analysis again and save the residuals. Oh, we haven't done the analysis, that was just the picture. Okay, let's do the analysis and save the residuals. Linear, our dependent variable is the advertised price, and the independent variable is the original price. Statistics, yep, plots, let's have those. Save, let's save our unstandardized predicted values and our standardized residuals, which are our errors. Okay, can't remember what options are. No, don't need any options. Okay, so we've got our output. You can see it's popped up 2 new variables. If you're doing several analyses on the same data set, you might want to go in and rename these because you lose track of what they were from. Let's scoot past the analysis and have a look at the, oh dear, so normality. If the data was normal, it would fall on the straight line. Clearly it has a major wiggle in it. So we can assume that this data is, the errors are not normally distributed, and this is a problem. If we look at the histogram, we can see that the problem is that it's too peaked. It looks like it's been pulled up in the middle. If you want to get a measure of this, you would be looking for kurtosis. We're not going to try and fix this, we're just going to comment on it. Now let's have a look at our other couple of plots which we have to generate ourselves. So a scatter plot where we have a look at our predicted car prices, unstandardized there. So these are the predicted car prices based on the original price and the errors in the model. And we want to know that the errors are independent and that they have constant variance. We're basically looking to see that they're randomly scattered about. And here we can see, hopefully it's clear to you, that they are not randomly scattered about. Now we do have these two outliers, and if you remember back to when we looked at this data set before, this was the cars that were bought very, very cheaply and sold for astronomical prices because they were done up as show cars or prestige cars, and they don't really fit with the rest of the data. So it's worth deleting these or removing them and running the analysis again. But even with them in there, I might change the Y scale so you can see it better. Let's change the maximum to 10. Even with those values in there, hopefully you can see that we're not getting the residuals randomly scattered about. There's a really clear pattern in here. There's very small amounts of variation with the lower prices, and the variation is increasing. So we have increasing variance or heteroscedastic variance, and what we want is constant variance or homoscedastic variance. And so this is the problem. We're not able to fix it in this subject, but we should be commenting on it. And the last plot that we would do would be the plot of the errors in the order they were collected. And this is probably more appropriate to experiments rather than observational studies, just in case something has changed over the course of the experiment. Let's say you were melting ice and the room got warmer over the afternoon and things started melting faster. Patterns like that will show up in the residuals. So we'll look at the line represents the standardized residuals, the errors, and we want to have a look at it by case number. Okay. And here we can see that they do seem to look, as far as I can tell, randomly scattered about. We've got this massively high one here, and these are the prestige cars. So you can, as an exercise, go through okay, the phone rang and I've lost track of what I was saying. So I'll assume that I have talked about this plot here, and I was going to, yes, you can go through and delete these if you like, and then run the analysis again. Okay, so the last one I want to look at quickly is a new data set, because I just wanted to pick out something that does happen in case you see it in your projects. Now this is part of a data set of bouncing balls on different surfaces and seeing how high they bounce, rebound back, and the time until they stop bouncing. Now I've just taken out one section of the data set because there was something interesting which happened with the golf balls when they were bounced on concrete. The whole data set is much bigger than this. It was quite a large experiment. So if we do the graph, so I'm going to do a scatter plot. Now I would like to see if I can predict the time until the ball stops bouncing by the height of the first bounce. Now I would expect that this would be a very close linear relationship, in that if it bounces, the higher it bounces the first time it rebounds, the longer it's going to take to stop. And I would think that that's a fairly straightforward relationship. Okay. Now it looks fairly reasonable from that. Let's put the regression line in. Linear, okay, close. Now you might be able to see that there does appear actually to be a little bit of a curve here. Now this will show up more if we have a look at the residuals. So if I go to Analyze, Regression Linear. Now I'm looking at the time until it stops bouncing based on the height of the first bounce. Statistics, yeah, plots, yeah, give me those ones. Might be able to get it to do the scatter plot straight from here. Let's do the Y. We would want the standardized. I think it's a little bit harder to see here, which is why I saved them out, but we want the Y to be the standardized residuals versus the predicted values. It's only got adjusted predicted values. I don't actually know what that is. Let's just do that. Okay. Okay. Very nice. So we can see that it's not completely normal and there's a bit of a wiggle here in the line. That's really not the major problem. The major problem is here. These residuals are not randomly scattered about. Hopefully you can see here that it really does look like there's a curve in these residuals. Now if we go back up to the scatter plot, now that you know the curve is there, you might be able to pick it out of the scatter plot. So you can see that the data points are below the regression line, then they're above the regression line, and then they're below again. So sometimes you can pick these relationships out just from the scatter plot. Usually they show up a lot more clearly when you look at the residuals. Now what we can do is, here we put in, if I double click, we put in a straight line, but if I go back to that and ask it to put in a quadratic line, which is a simple curve, if you remember back to high school mathematics, this is just adding a squared term in, apply, close. Now it's actually, I'll just close out of that, it's actually put both the lines on top of each other. I want to move that label. Not that one. I can't move it. Anyway, so you just have to put up with them on top of each other. So it's actually generated a quadratic regression here, and it's added in a squared term. I don't really expect you to do this, but if you do see the curved data, this curve pattern showing up in your projects, come and see me and we will sort this out together. Now what you can see is that visually, hopefully you can see that that line is fitting through a lot more nicely, and if you went through and did all the residuals, you'll see that all of a sudden that fixes a whole lot of problems. And the other interesting thing is that the R squared value goes up. So whereas with the simple linear regression we were explaining 88.5% of the variation in the data, now we're explaining 94%. So that's showing that we've got a much better fit of the data with this curved line rather than the straight line. So if you see a curved pattern showing up in your project data, come and see me and we will work out how to get this squared term in and hopefully fix up your regression. And here's the full output which you can look through when you do the regression analysis for yourself.